Today we want to talk about complex numbers. It's one of those situations in math where we come across a thing that we can't do and decide that it's unacceptable that we can't do it, so we just try to do it anyway. Here's the thing about complex numbers. Here's why we have complex numbers. When we look at this, the square root of a number, if I think about something like the square root of -4, I think what number, when multiplied by itself, will get us -4, and no real number will do this. So this square root of -4 we know is not a real number. This is not a real number. So in the early part of our training, when we learn about square roots and we see the square root of a negative number, we say this is not a real number. We just stop it right there. This is not a real number. Move on. And we don't say there is no answer. We don't say something like undefined. We just say it's not a real number. It's not defined for you, yet you don't get to know. So that ends today. So we say this is not a real number. The reason it's not a real number is that if we're looking for a number such that when I multiply it by itself, if I take two copies and multiply them, I'm supposed to come up with -4. And we can't do that because if I multiply two things with a positive sign, it's positive. And if I multiply two things with a negative sign, it's negative. So the problem is, when we square a number, the result is always positive. Because I'm taking two copies of the number and multiplying them, those copies have the same sign. So if I take 2 times 2, that's a +4. And if I take -2 times a -2, I get -4. Squaring a number means multiplying two copies of the number, and the two copies of the number have the same sign. The factors always have the same sign. So the product is always positive. Negative, I meant positive. Yikes. The factors have the same sign, so the product will always be positive. So not happy with this, we say, well, what if we invent an extra number that's not one of these regular numbers, such that when we square it, we do get a -1. So we invent the imaginary unit. So we invent this number, like I was there. We say I is the square root of -1. It's bad grammar. I am the square root of -1. That is, I squared is equal to -1. This is a number, clearly not a real number, because no real number can do this. I, the imaginary unit, is a number such that when you square it, you get -1. Clearly, I is not a real number. Bad grammar. Clearly, I am not a real number. Because no real number does this. And we decided to call it imaginary. I think before this idea, we just said numbers, and then this kind of highlighted the need for like two different kinds. We needed to split our numbers up. I don't know, I have to go back to old math classes before they had things like square roots of -1. So then the question came up, it's like, well, is this going to be useful? It's like, I don't know. It'll help us simplify things like the square root of -4. So now if I want to figure out the square root of -4, I could say this is the square root of -1 times the square root of 4. The square root of -1 is I, and the square root of 4 is 2. So now we can say that the square root of -4 is 2i. Since I is written as this letter and the 2 is a number, we usually write it as a coefficient. Unless we can't simplify any of the radical parts. So if I had something like the square root of -7, that's going to be the square root of -1 times the square root of square root of 7. I would just write the I in front of the radical. If I have a variable with a radical as a coefficient, I don't want it to look like the variable part, or in this case, the I is part of the radical or under the radical. So I'm just going to write I times the square root of 7. And if I'm simplifying my radical, and it has some whole number part and some square part and some non-square factors, then I just sandwich the I in between. So if I had, for example, the square root of -28, I'd say this is the square root of -1. There's a square root of 4 that we can simplify, and there's a square root of 7 that we can't simplify. So I'd square root of 4 is 2, then I'd write the I, and then the square root of 7. We just don't want it to look like the I is under the radical. I don't want to write down the square root of I. So neat, we've got this thing here. We've got this object. So once we kind of sort it out, it's like, okay, this is how we're going to work with this I, this square root of -1. We started looking for places where this might show up. And one of the places that shows up is in quadratic equations. So if we think about the quadratic equation x squared minus 4 equals 0, if we want to solve this equation, now we're thinking in terms of solving equations. X gets squared, and then we subtract 4 and we come up with 0. That means the x squared part on its own has got to be a 4. And then when we take the square root, x can be positive or -2. There are two solutions. 2 squared is 4 minus 4 is 0. -2 squared is also 4 minus 4, also 0. So there are two solutions to the equation. before, we had these imaginary units, when we looked at this quadratic equation, x squared plus 4 equals 0, we would try to do the same thing. Subtract 4 from both sides, just like we added 4 from both sides here. But then we ended up with x squared is equal to -4. And we're like, no real solutions, right? This equation does not have real solutions. But now with these imaginary units, we can take the square root of both sides. The square root of -4 is 2i. So now with imaginary units, I can say x is equal to plus or minus 2i. So it looks like we're going to be able to solve some quadratic equations that we couldn't solve before. So here's our initial thing. We looked at square roots of negative numbers and say, well, that's not a number. There's no number that does that. So we invented one that does that. And we are all solving quadratic equations. It's like, we get solutions here, but we get no solutions here. But now that we've got this new technology of the square root of -1, it's like, well, now we can solve these kinds of equations. Now, if we take a look at the graphs of these two functions. So the graph of x squared minus 4 is a parabola. I do that entirely too high. We know that the solutions to the equation x squared minus 4 equals 0 are going to be represented by the x-intercepts of the graph of y equals x squared minus 4. That's the relationship between the picture, the graph, and the equation. That's the relationship between the graph and the equation. So here's the +2, and here's the -2. That was lucky. So our real solutions to x squared minus 4 equals 0 show up as x-intercepts. But on the graph of x squared plus 4, on the graph of x squared plus 4, instead of having a vertex at 0, -4 like we had over here, our vertex was way up here at 0, 4. The x-intercept, the x-axis was way down here. No x-intercepts. So the graph of y equals x squared plus 4 has no x-intercepts. Because the equation x squared plus 4 has no real solution. X squared plus 4 equals 0 has no real solutions, only complex solutions. Well, I'm going to say no real solution. We might say that the function itself has no real zeros. Question? So the fact that we were looking at a parabola that did not have any x-intercepts means our equation has no real solution. So this is telling us that we don't have real solutions. No x-intercepts, no real solutions. X-intercepts, real solutions. So we have to see that we can't see there are solutions to this equation, x squared plus 4 equals 0. We can't see them because they aren't real. The solutions exist, they're just not real. Mathematicians wonder why people don't like us. At least our words mean something. Any questions? So the solutions exist, they're just not real. From the mathematics. So what if things are moved over? What if this parabola, instead of having a vertex at 0, 4, we move the vertex over to say 1, 4? We need more space. I'm going to shift the vertex over to 1, 4. we can still see by the graph that we're not going to have any x-intercepts, so we're not going to have any real solutions. So right away, we can see that there are no x-intercepts. So we'll see no real solutions. Let's write down what the graph of this function will look like. So instead of y equal x squared plus 4, since I've shifted over 1, I'm going to put in a horizontal shift of 1 to the right, then square, and then add 4. Now, if we set this equation equal to 0 and look for the zeros of the function, so if I take x squared or x minus 1 squared plus 4 and set that equal to 0, I'll subtract 4 from both sides. Then take the square root of both sides. This is where the plus or minus shows up. And I'll have x minus 1 is equal to plus or minus 2i. And then we can add 1 to both sides. So our solutions are not real as expected, but complex. 1 plus or minus 2i. Interestingly, we still get 2 solutions, and they're still evenly spaced about the vertex. We still have 2 solutions, and they're still symmetric about the vertex. If we think about a parabola with the vertex at 1, negative 4, we can see from the graph that there are going to be 2 x-intercepts, so we're going to have 2 real solutions. This equation, or the equation for this parabola, will be y equals x minus 1 squared, but this time minus 4. There's the vertex of 1, negative 4, rather than 1, positive 4. And if we set this equal to 0, now we're going to add 4 to both sides, so x minus 1 squared should equal positive 4. So x minus 1 should equal to plus or minus positive 2, or regular 2, real 2. So our 2 solutions are 1 plus or minus 2. When we had 1 plus or minus 2i, those are not like terms. I can't combine them. But now I've got 1 plus 2 and 1 minus 2. And that's where my x-intercepts are, 3, 0, and -1, 0. Because we're fancy trig students, we knew that this is where the zeros were going to be because I just took my parabola with zeros at -2 and +2 and shifted 1 unit to the right. -2 went up 1 to -1, and 2 went up 1 to 3. So I just took the whole graph and shifted 1 unit to the right. Once again, 1 was in the middle, but now the x-intercepts are evenly spaced around their real numbers. Where the previous one was still in the middle, but it was ±2i. So they had an imaginary part for them. Any questions? Well, now we sorted something out. We can now solve any quadratic equation. A quadratic equation with real coefficients will always have 2 solutions. They just might have an imaginary part for them. So now I've got an entirely different kind of number. I've got a number that's combining a real part and an imaginary part. So we're going to call that a complex number. A complex number has a form a plus bi, where a is a real part and b is the imaginary part. So a real part and an imaginary part. Now I've got a whole extra set of numbers. All because we looked at square root of -4 and said, that's not a number. And someone said, well, what if it is? I can imagine a bunch of mathematicians sitting around and they like get high. I go, man, that's not a real number. And one was like, oh, yeah, man, but what if it is? Let's make one. Let's talk about dealing with complex numbers. Make some complex numbers. Let's take a complex number. Let's say, let's grab this one, 1 plus 2i. And let's make another complex number. Let's say -3 plus 4i. A complex number has a real and an imaginary part. So here's two complex numbers. They both have real parts and imaginary parts. And let's suppose that we wanted to add these together. And let's suppose that I said I was going to flunk you in this class unless you guess how to add these numbers. I'm not. That would be pretty messed up. To force you to guess on something that I haven't told you how to do and then flunk you for not guessing. Although, always guess. The only thing we got sometimes. So think about what you would just guess you would want to do to add these things. If you were thinking, I would just make -2 plus 6i, you are correct. You just add the real parts and add the imaginary parts. Because you've been programmed with algebra, and programming with algebra includes combining like terms. They're like, oh, what if I just did like terms? That's exactly what you would do. Just do like terms. So now that we're just going to do like terms, if I ask you to subtract these complex numbers, you're just going to add the opposites. I don't know if you think add the opposites. I'm not allowed to read your minds anymore. So minus a -3, you just change the signs. Minus a +4 is -4i. And then just add. 1 plus 3 is 4. 2 minus 4i is -2i. Is what you would have guessed. If I force you to guess, it's what you would have guessed. Let's suppose I asked you to multiply. If I asked you to multiply these complex numbers based on what we did before, what would you do to multiply them? I'm thinking of a 4-letter F word. FOIL. That's how we multiply binomial. I was thinking of another one. Oh, we got another week. But FOIL, yeah, that's more appropriate. That's definitely more appropriate. You just do 1 times -3, 1 times 4i, 2 times -3, -6i, and then plus 8i squared. Then we would combine like terms, -3 minus 2i plus 8i squared. Now we're looking at this and we're like, oh, dude, that does not look like a complex number. Complex numbers are supposed to be like, well, a plus bi. You didn't say nothing about no I squared, but that's okay. Because I squared, we can simplify. I is defined to be the square root of -1. And what that means, on our previous page, we had it written down. What that means is that I squared is -1. This doesn't autofocus. Whoa. I squared is -1. So that I squared we can simplify. So it's going to be -3 minus 2i plus 8, and then I squared is -1. So now I have -3 minus 8 is -11. Color coding again. No. Maintain that. -3 plus 8 times -1 is -11 minus 2i. So here we're just using the fact that I squared is equal to -1. So our product is another complex number. So we can simplify to I squared. Got another operation. You're probably expecting division because that seems to be the natural thing, but you're probably not expecting exponents because nobody expects exponents. But we've got this binomial 1 plus 2i, and I want to square it. So we're just going to do the same thing we did last time. This just means take the thing and multiply it by itself. So I'm going to take a 1 plus 2i and multiply it by another 1 plus 2i. So that's going to give me 1 times 1 is 1, plus 2i, plus another 2i, plus 4i squared. I can combine the 2i and the 2i to a 4i, and this 4i squared is a negative 4. This I, because I squared is negative 1. So I end up with 1 minus 4 is negative 3 plus 4i. Yeah. That was just FOIL. So I was going to first outer inner last that. So 1 times 1, outer is 1 times 2i, 2i times 1, 2i times 2i. Division is weird. So that one I would not ask you to guess on. Division works out weird. But if you wanted to divide, technique for division is weird. What we do is we multiply by the conjugate of the denominator on the top and bottom. For division, we multiply by the complex conjugate of the denominator. So in the end, we have to FOIL on the top and the bottom. So this is the technique to divide complex numbers. We multiply by the complex conjugate of the denominator. This is why. Multiplying out the numerator, that's just normal. 1 minus 3 times -3 is -3, minus 4i, minus 6i, minus 8i squared. That's all working like normal. The I squared is -1, just like it was before. And so that -8i squared is +8. -3 plus 8 is 5. And then we have a minus 10i. The reason that we're going to multiply by the complex conjugate of the denominator is an interesting thing will happen. We'll have -3 times -3 is 9. -3 times -4i is positive 12i. 4i times -3 is -12i. The imaginary part drops out, and the other part is negative 8i squared, or 16i squared. So when we multiply a complex number by its complex conjugate, which just means change the sign of the imaginary part, then the imaginary part drops out. This minus 16i squared is plus 16, and 9 and 16 is 25. The product of a complex number and its complex conjugate is real. And then we can divide 5/25 is 1/5 minus 2/5 I. This makes the imaginary terms cancel, so we get a real number in the denominator. We just separate out into our complex number form, a plus bi. So we might be thinking, this seems like calculator stuff, but this is like calculations. This is like calculations, and it's not what we have calculators for, and it is what we have calculators for. So if I ask my calculator what the square root of -4 is, right now it says non-real answers, right? Because right now my calculator is sitting at the algebra level before we've learned about the imaginary unit. So if I go to my mode and I scroll down, that's because it's only looking for real numbers. So what I want to do is switch it over to a plus bi form. Now my calculator knows what complex numbers are. So now if I ask it for the square root of -4, it tells me that that square is 2i. Now, if I want to multiply some complex numbers, like if I want to say -1, sorry, it's +1, 1 plus 2, I need an I. So notice that above the decimal point is where we find I. That's its second decimal point. That gives me an I. If I want to multiply 1 plus 2i times -3 plus 4i, That gives me the negative 11 minus 2i that we had on the previous page. And if I want to divide, I take 1 plus 2i and divide by negative 3 plus 4i. That gives me my 1/5 minus 2/5 I. If I want that as a fraction, there's 1/5 minus 2/5 I. Any questions? It's just another system of numbers that sits above the real numbers. Let's take a pause, come back and talk about roots. That's another operation that we need to deal with.